Okay, so here are my predictions. We probably could dig in a little further, but this is a really nice set of things to start with, okay? So I'm hoping whatever I get at the end is going to meet these conditions. Let's start working. Here's my start off point. I don't know anything apart from these things, which are sort of general conditions. I don't know anything about this, so I'm going to take advantage of what I just established before and go after this guy. Now we do know the derivative of tan x, right? If y equals tan x, then the derivative is equal to, how's your memory? It's going to be sec squared, right? And you can go ahead, you can do the quotient rule on sine on cos, you can go ahead and get that result. Sec squared x. So far so good. Now what I want actually, that's not really what I'm going for. I want the derivative that's the reciprocal of this, right? Because I'm after this tan inverse business. So I'm going to take the reciprocal using this property up here. Dx on dy equals 1 on sec squared x. Now, let's just pause for a second. Sec squared, of course, is, what is sec squared? It's 1 over cos. So this, I've just written 1 over cos squared. I could have written cos squared, but I'm actually not going to. It's not useful to me to do that because, just think about this for a second. I have the derivative, but it's not in a very useful form to me at the moment. It doesn't yield me much insight, it's hard to work with. Okay? So I want to sort of massage it a little bit until it's a little more helpful, until I can see if it follows these conditions or not. Okay? So I'm going to come over to this board. How can I work with this? Well, the original function is everything in terms of tan. Agree? Tans. Okay. So here I have sec squared. What piece of knowledge do I have that helps me translate back and forth between sec and tan? Yeah.
Identity 1 plus tan squared.
Yeah. Very good. Now you might be, just got all these things bubbling around in your head, and you know what the sec squared tan squared identity is. I don't. So I'm going to go back to this guy, but sine squared x plus cos squared x. This is the actual Pythagorean identity. Equals 1, from which you can get all the rest of them by dividing through by whatever you like. Okay? Now I want to get tan squared and sec squared in there, so what shall I divide through by? Cos squared will do it, right? So let's just go ahead. This is going to become tan squared, right? The cos squared is going to become 1. And then as we just established, the 1 will become sec squared. Very good. Okay, so seeing as that is the case, therefore, I come back to this guy and I say, therefore, dx on dy is equal to, and I make my substitution for sec squared. I'm going to write it in reverse order just because it's kind of the, it's kind of a convention and it fits other patterns we'll establish later. Now, this is good, this is better, because I know what tan x is. The first line I wrote down was my definition for tan x. It's y. Right? And that's kind of nice because this is a derivative with respect to y, right? Usually you differentiate with respect to x, everything's in terms of x's. Well, now I'm differentiating with respect to y, so this is my result. Okay, I'm almost there, and then we can check our predictions. This is all a bit weird because this line I've written here has everything kind of in the reverse order, right? I'm used to thinking like y equals whatever, I make that the subject. So all I have to do to translate from this, just so it's a little more normal, is just to take all my inputs and outputs and swap them, right? So this is if x equals tan inverse of y. If on the other hand, y equals tan inverse of x, I've just swapped my y's and my x's, my inputs and my outputs, then I'm going to swap the x and y here, upside down. And here, I just swap that y that's there for an x. Ta-da! Now, let's think. Does it work? I'm expecting, we originally predicted that f dash, this guy, would always be positive because tan inverse is an increasing function. Does it match? It does, because of course, no matter what value of x you put in there, this guy's going to be positive. So you've got a positive divided by a positive, thumbs up. What else have we got? X equals, can satisfy any real value. Can I put anything in there? Yeah, normally when you have rational functions like this, you think, ooh, do I have any vertical asymptotes? This thing will never have a vertical asymptote. Why? Because x squared, we're dealing with real numbers, right? So the smallest x squared could possibly be is 0. So therefore the smallest this could possibly be is 1 over 1, right? Sorry, the smallest that the denominator could be, so therefore the biggest that the whole number could be. Which leads to our next issue. Even function. Is it even?
Yes.
Yeah, because you look at the power, that's all you need to know. Does this work, this particular thing? And the answer is yes, because the larger this gets, your denominator skyrockets, so the whole thing approaches 0 at your extremities. Yes? Last one, test at 0. Thumbs up, 1 over 1, which is in fact the greatest the gradient will be, right? That was nice. Well done. Okay. So what did we take advantage of? Just rewind a little bit. We really need to establish this. So we did that before we thought about trig functions, and inverse trig functions. We had to go through here. We needed the derivative of this, clearly, okay? But this was putting those two pieces together, was our bridge to get to our derivative of this. You had to be a little careful with your identities here. And then out leaps this answer, which is really, really nice. By the way, just really quickly, you might like to draw a really brief sketch of this. This gradient function, what does it look like? A nice easy way to think about it is, it's a reciprocal of a function I'm very, very familiar with, right? 1 plus x squared, how would you verbally describe that? What kind of family of curves is it in? It's a parabola, it's concave up, and it's been shifted 1 unit. So here's 1 plus x squared. To take the reciprocal of this, I know that that's 1. What's the reciprocal of 1? 1, okay. So 1 over 1 plus x squared also passes through that vertex. And then the rest of it, well, this guy over here is skyrocketing, but he's on the denominator. So he just drops down like that towards 0. And because it's an even function, there you go. Okay, so that green line there, that's the gradient function of tan inverse, which exactly matches what you predicted.